Planet Earth, a jewel in the darkness of space. Our home is timeless, beautiful, and incredibly violent. Volcanoes are one of the most powerful natural phenomena on the planet. They create new land, destroy the old. They blast out gases that transform the air we breathe. Deep in our oceans, volcanic heat fuels strange new life. Volcanoes help power the living Earth. Now, we search for signs of life on alien worlds. We know life needs water. We know it needs energy. And that's where volcanoes come in. They pump out vast amounts of energy. Find volcanoes on other worlds, and we might find life. The search starts here, the planet orbiting closest to Earth, Venus. A world that appears very much like ours. Venus and Earth are roughly the same mass. They're roughly the same distance away from the sun. So they're kind of like twins. 3 billion years ago, Earth and Venus were very similar. New land, new oceans, an atmosphere. Both planets were perfect for life. But on Venus, something went wrong. Something made Venus diverge radically from the history of Earth. Venus took a definite turn to the dark side a long time ago. Venus is a hellhole, our evil twin. Today, Venus's surface is like a furnace. It's 900 degrees Fahrenheit on the surface, and it's hot enough to melt, actually, some metals. So you wouldn't stand a chance. Venus is a greenhouse world. Its atmosphere is thick with carbon dioxide. It traps heat from the sun like a blanket. These actual images of Venus's surface reveal a barren, superheated wasteland. Venus's thick blanket of CO2 killed the planet. The CO2 came from volcanoes. Orbiting space probes gave the first clues. Radar punched through Venus's thick clouds and revealed volcanic formations across the planet-like formations we also see right here on Earth. The shield volcanoes of Hawaii. Shield volcanoes get their name from the round, flat shape. These volcanoes ooze, but they ooze for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we started to study the landforms there, and we saw a lot that was actually very familiar. In particular, we saw giant shield volcanoes that are very similar to the shield volcanoes here in Hawaii. The radar images of Venus were dead ringers for the shield volcanoes on Hawaii. Sometime in the past, Venus had volcanoes. For the first time, we had had a picture of Venus revealed, and boy, were we shocked. We found a scarred surface, a volcanic surface. There are at least 1,000 volcanoes that are very large, and maybe tens or even hundreds of thousands of smaller ones. 3/4 of Venus's surface is lava plains, evidence of an ancient cataclysm. This could have been a home for life. Instead, it was engulfed by fire. Volcanoes belched trillions of tons of carbon dioxide into Venus's atmosphere. Temperatures soared. The seas boiled dry. A runaway greenhouse process began. On Earth, carbon dioxide is able to absorb into the rocks. It's able to absorb into the ocean. But on Venus, you have no water. And it's now so hot that carbon dioxide can't even combine with the rocks. So as carbon dioxide was released into the atmosphere of volcanoes a long time ago, over time, there was less and less of a method to take it back out of the atmosphere. If Venus ever had life, volcanoes sterilized the entire world. Earth remains the only living world we know of. That may change. This is the gas giant, Jupiter. Its moons, frozen and dead. or so we thought. Look closer, and a mystery emerges, a cloud hanging over a cold and lifeless world. On Venus, volcanoes turned an Earth-like world into a superheated hell. Finding volcanoes on an Earth-like world was no surprise. But spotting volcanoes on a moon was a shock. In March 1979, the Voyager 1 space probe gave us our first close-up view of Jupiter's tiny moon, Io, a world we once thought cold and dead. And they saw something really weird. They saw this arc next to the moon, and it looked almost as if there was another moon behind it. And we scratched our heads and said, well, what could that be? Everybody knows that Io is dead, boring, uninteresting. And then people realized, oh my God, it's a volcanic eruption. We found that it's covered with volcanoes. It is tremendously geologically active. There are volcanoes erupting all the time, and what they're erupting is a lot of sulfur. And it gets very hot. And sulfur, when it changes temperature, changes color. It can be red, or orange, or yellow, or black. And so these pictures of the face of Io make it look like a pizza covered with different kinds of cheese and olives, where the little black spots are. Io is not dead. It's alive and kicking. It has over 400 active volcanoes. The largest plume erupts from a gigantic lava lake. It reaches nearly 250 miles into space. If we could stand on the edge of that lava lake and watch that plume shooting off into the blackness of space, that would be an incredible sight. Io's eruptions are so huge because Io is so small. There's nothing to hold the lava back, virtually no atmosphere, and very little gravity. These fast eruptions make Earth volcanoes look like firecrackers. How can such a tiny moon be so volcanic? The answer is Jupiter. Just as the moon raises tides in Earth's oceans, Jupiter raises tides on Io, tides of solid rock. Io's orbit around Jupiter is not a circle. Sometimes it's closer, sometimes farther away. Jupiter gives Io a gravitational pounding. And so, Jupiter's gravity pulls on it a little bit harder, and a little bit weaker. And what happens is the moon stretches like this. It's called a tidal force. And it doesn't stretch this much. It's only a little bit. But in fact, it's enough to heat it up. It's just friction. It's the same way when you rub your hands together really fast. They begin to feel warm. Friction creates heat. Jupiter's gravity stretches and squeezes Io. In every 2-day orbit, the ground rises and falls by nearly 300 feet. This tumbling generates intense heat and gigantic pressure. Wherever there's a weak part in the crust, the lava rushes out. So the volcanism is on a planetary scale. Unlike here on Earth, where there are certain bits that are active around the plates or in weak spots, this is an entire moon that's one active hotspot. Thanks to the incredible power of gravity, Io is the most volcanically active world in the solar system. The volcanism on Io taught us something new. It taught us that internal sources of energy can drive volcanism in a way that's different from that on Earth. In outer space, tidal forces, the differential squeezing of the moons of a gas giant can, also create volcanic activity. That was a game changer. Io is a lava world, superheated and violent. It's hard to imagine anything surviving there. Yet, the volcanic principle here is the same as on Earth. Pressurized, superheated magma below the surface blasts through fissures in the crust. But not all volcanoes need magma. They don't even need to be hot. travel out past Jupiter into the outer solar system, and it gets cold, really cold. The distant moon. Triton is so cold that much of its tenuous atmosphere can freeze solid. Yet there are volcanoes, here are volcanoes, that may hold the secret of alien life. We think of volcanoes as mountains of solid rock. Deep beneath, rock is so hot and pressurized that it bursts violently out as lava. But not all volcanoes work this way. There are volcanoes on other worlds that don't use molten rock at all. Right at the frontiers of the Sun's planetary system, Triton orbits the ice giant Neptune 2, and 500 million miles from the Sun. The temperature is a frigid 390 degrees below zero. When NASA's Voyager probe flew past, it revealed a world covered mostly with frozen nitrogen ice. But the probe found something else. When Voyager flew by, it saw these black smudges. And all of the smudges were going in one direction, almost as if there was a wind blowing dark material dust in one direction. Signs of activity on a world so cold it freezes nitrogen. Volcanoes at almost 400 degrees below zero. Forget molten rock. Triton spews out a mixture of nitrogen and moon dust. And the geyser not only has liquid nitrogen, which is in a fluid form, but also sort of dusty stuff that's lighter, that can even go further in the weak winds. So you have this wonderful sort of double plume of an icy area, and then a darker, smudgy area, basically made of dust, like moon. Dust. Triton's surface is nitrogen ice. Underneath, there are lakes of liquid nitrogen. How? Scientists believe it's because nitrogen ice lets light in, but doesn't let heat out. There's almost a bit of a greenhouse effect going on Triton, that there's a layer of nitrogen ice that's transparent. And just like a greenhouse here on Earth, when you have glass, light can pass through it, but then the heat is trapped by the glass. The sun shines through the surface and warms the nitrogen beneath. Just a few degrees is all it takes to turn nitrogen ice into gas. The temperature gradient, a change in that temperature, that's what's important. And that's enough to melt the nitrogen underneath the surface on Triton and have it burst through as a geyser. This is a cryovolcanoso, cold, that the material erupts would freeze water as hard as rock. The solar system is more active than we ever imagined. We have found weird eruptions on many planets and moons. But so far, the only world where volcanoes are linked to life is ours. Or so we thought. This is Europa. It orbits Jupiter, nearly 500 million miles from the Sun. A frozen 2,000 wide, rock-hard ball of ice. From a distance, its surface looks smooth. Up close, it's a different story. Jupiter's enormous gravity gives Europa a pounding, just like its neighbor, Io. The surface heaves and flexes, creating rifts and deep crevices. When we first got close-up images of Jupiter's moon, Europa, they looked a little familiar. And it turns out, it looks like ice floes that you see when you fly over the Arctic. And it turns out, it's the same thing. Europa has a several-mile-thick shell of ice on its surface, and beneath that is a global liquid ocean. Magnetic readings suggest Europa has an ocean that's a staggering 60 miles deep. Jupiter's gravitational pounding heats the rocky core and melts the ice above. It's not unreasonable to think that as the core is being stretched by tides and heated up, possibly even molten, there's some boundary between a hot core and a liquid water ocean. On Earth, underwater eruptions are surrounded by life. The same could happen on Europa. Here, the darkness is total. The pressure, a crushing 2,000 Earth atmospheres. A brutal world, but perhaps a cradle for life. If life got off the ground here on Earth, why not on Europa? All the ingredients are there. An energy source, volcanic activity, a universal solvent, liquid water, a rich hydrocarbon chemistry. We have this mixing bowl of ingredients that happened on the Earth 3.5 billion years ago. And we have similar conditions on Europa. So some people are saying, if it happened here, why not there? Life on Europa would be hard, but not impossible. On Earth, there is life at every extreme: searing heat, crushing pressure, total darkness. Alien life on Europa might look surprisingly similar. If life exists under the ice cover of Europa, they would be aquatic, but without eyes, because there's no light to speak of. They would probably use sonar in order to make sense of their surroundings, organisms that literally feed off the energy from the volcano. On Europa, volcanoes could be the source of new life. It's even possible that Europa is normal, that this is how worlds with life generally are. Earth could be the exception. Think of it, Europa could be a template for billions of moons out there that have liquid oceans on them. So, all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. What a shock. Our solar system alone has over 170 moons. Multiply that across the universe. And that's a lot of places where life might take hold. All it takes is liquid water and a source of energy. Potentially, volcanoes provide both. And they are everywhere. This is Saturn twice as far from the Sun as Jupiter. Yet it too has volcanic moons. And just like Jupiter's Europa, these moons could harbor life. This is one of the strangest worlds in our solar system. Saturn, a ring system 600,000 miles wide, an amazing 62 moons, and one with a secret Enceladus. Enceladus is one of Saturn's smaller, more distant moons, and it's been known for a long time that it's covered in ice because it's very bright, very reflective. But when the Cassini spacecraft went there, it discovered something amazing. The Cassini probe revealed something incredible, not on the planet itself, but on Enceladus. Backlit by the sun, a gigantic plume bursts out into space, a sure sign of volcanic activity. It was an amazing discovery, and it helped answer a question that has puzzled scientists for decades. The mystery of Saturn's E-ring. Saturn's outermost ring is vast, almost 200,000 miles across. And it shouldn't exist. The ice particles that make up most of the ring are too far from Saturn to stay in orbit. They constantly drift away into space. Something replenishes the ring. The ice volcanoes of Enceladus. Those plumes that are ejected from Enceladus's south polyide turns out that those are going into space. And they're not just going away. They're feeding a ring around Saturn, the E-ring. So this little moon is giving something back to its parent planet. Water blasts from Enceladus's volcanoes, hits the vacuum of space, and instantly freezes into tiny ice crystals, creating the vast E-ring. One mystery solved, another replaces it. What creates the volcanic plumes? Cassini's cameras zoom in on the moon's south pole, and capture these huge chasms, scarring the surface. There are these wonderfully huge cracks at the south pole of Enceladus. And as Enceladus goes around Saturn, these cracks open and shut as the tides go by. Now these cracks are huge. They're hundreds of miles long. And when they begin to open, you would have this big crevasse opening at maybe 100 miles an hour down the length of that. It'd be incredibly spectacular. Huge gravitational forces crack the surface open and closed at enormous speed. Like Europa and Io's orbits around Jupiter, Enceladus's orbit around Saturn is elliptical. This helps generate the heat to melt ice and create oceans of water beneath the surface. The conditions of the water underneath Enceladus's surface are absolutely perfect for life. It's the right temperature. It'd be a good pressure for life. Liquid water would be just like seawater here on Earth. And the chemistry of the water we see shooting out of these vents suggests that it is very similar. There's salt. There's organic material in it as well. So we have identified a place in the solar system where there very well may be life right now. Cassini has detected complex carbon molecules in the ice plumes. Combined with liquid water, these suggest that just maybe life could survive deep within this enigmatic moon. Enceladus may not be alone. Another of Saturn's moons might also harbor life. Titan, one of the largest moons in our solar system, the only moon with a thick atmosphere, a frozen world, ice as hard as rock, lakes of liquid methane. Yet here too, we might find evidence of volcanoes and the tantalizing prospect of alien life, a raging inferno on the surface of Io, eruptions of ice and nitrogen on Triton. Volcanoes are one of the most destructive forces in our universe, but out of annihilation comes the possibility of life. Even here, on Saturn's mysterious moon, Titan. It's 3,000 miles across, larger than the planet Mercury. It's the only moon in our solar system with a thick atmosphere. There is weather here, storms, winds, rain, even lakes. All so cold that liquid methane takes the place of water. And it's loaded with chemicals that life needs to survive. Titan has turned out to be absolutely one of the most interesting places in the solar system. It's an active world. It's the only moon with a thick atmosphere, very much like Earth, because it's mostly nitrogen. And it turns out, an atmosphere loaded with organic molecules. Methane gas, high in Titan's atmosphere, reacts with sunlight and creates the kind of chemicals life depends on. But if sunlight converts methane into organics continuously, why doesn't the methane run out? The atmosphere is full of methane, and yet we know methane is being destroyed by sunlight on a short time scale. So it shouldn't be there. There needs to be a source of methane. Something on Titan pumps out a continuous supply of methane. Cassini has detected what looks like a crater. Its interior is as deep as the Grand Canyon. Infrared cameras reveal different types of material surrounding the crater. Scientists believe the green areas could be volcanic. Perhaps plumes of lava ejected from Titan's interior, if it exists. Lava, Titan style, is a super chilled icy slush. But compared to the rest of Titan, even ice slush is scalding hot. On Titan, the hot liquid spewing from volcanoes might be ammonia or water. Normally, those are frozen solid on the surface. But if they're heated beneath the surface somehow, they could erupt. Down on Titan, What comes out of volcanoes is methane and ethane. And that's probably the reason why we have this very thick cloud cover, this orange haze around Titan. This haze probably came from outgassing from the volcanoes of Titan. Even for volcanoes, on a world as cold as Titan, you need heat. That's what turns ice into liquid and generates eruptions. On Titan, that heat has two sources. Radioactive materials warm the interior, and Saturn's huge gravity massages the moon, just like Enceladus. These two forces generate enough heat to turn ice into water, and liquid methane to gas. We think of volcanoes as being hot, and ice as cold. And yet, if you're out on Titan, where you're 1 billion miles from the sun, and it's quite cold, then those flows of just barely above freezing water ammonia ice, they might be the hottest things around. So, hot is a relative term, depending on where in the solar system you are. Could volcanoes on Titan give life a chance to survive here? Life as we know it needs an atmosphere, a solid surface, liquid water, and the heat to drive chemical reactions. On Titan, volcanoes could provide them all. If you have a volcano on Titan, you'll have heat added to that, and all of a sudden, you'll have liquid water surrounded by organic material. I mean literally, anything you need for the start of life. If life does exist on Titan, it would be truly alien. It would breathe hydrogen in place of oxygen, perhaps swimming through lakes of liquid methane at 300 degrees below zero. Perhaps there are oceans of ethane. Perhaps they are tide pools. And perhaps volcanic activity and hydrothermal activity. Perhaps they're hot springs. Perhaps volcanic heat could generate enough to get life off the ground in Titan. That's a speculation, but it can't be ruled out. But we may not need to travel this far to find signs of life. We may find it on a volcanic world much closer to home, the red planet, Mars. Volcanoes are everywhere across the solar system. Worlds like Io, Titan, and Triton are complex, dynamic, and violent. Once we thought that Earth was the only planet with volcanoes and with life. Now we find volcanoes everywhere, but we have yet to find alien life. Volcanoes embody the sheer power of creation and destruction, and they go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. In the cauldrons of volcanoes is the origin of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, replace the old with the new. If volcanoes are bound up with the processes of life, then where is the life on other worlds? Perhaps the answer originates in deep time when the solar system was young. On a young planet, much like our own. This is Mars. 3 billion years ago, it had active volcanoes. One still remains the largest volcano in the solar system. The cliffs leading to it are over 6 miles high. Mount Everest would sit comfortably in their shadow. And those are just the foothills. This is the awe-inspiring Olympus Mons. It covers an area the size of Arizona. Its crater alone is 53 miles wide. A Goliath forget. On Earth, the crust is always moving. Deep below, a single hotspot pushes magma through the surface, building a new volcanic island. But while the hotspot stays still, the surface is moving. The new island moves away from the hotspot, and a new volcanic island takes its place. Mars is different. The crust is locked, solid. On Mars, there's just none of that tectonic activity. The crust as one big solid plate. And so, if there's a hot spot, it just sits there and builds and builds and builds. You get a bigger and bigger and bigger volcano. And that's why Olympus Mons is so huge. Olympus Mons today is a frozen relic of a distant, warmer past. Mars' shrunken atmosphere means that Olympus now reaches almost into space. A true colossus, an extinct volcano on a dying world. But Mars' ancient volcanic terrain could one day harbor life again. The evidence is right here on Earth. On Hawaii, volcanoes have created mysterious tunnels called lava tubes. Channels left behind when torrents of molten rock surge into the sea. But some are now empty, and that offers us an opportunity. Lava tubes are formed when you have an underground river of hot basaltic lava, 2,000 magma, molten rock. And picture it like a frozen river of water, with the ice crust forming on the top. It's the same thing, only here, the crust is solid rock, and the river keeps flowing underneath and makes this cave, this lava tube. Extraordinary recent images suggest Mars's volcanoes also may have created lava tubes. Any planet with basaltic volcanism, any rocky planet, will probably have lava tubes. And now, we've found a couple of them on Mars, in places where there are skylights, places where the roof has collapsed. And you can see from orbit right into those lava tubes. If some tubes have collapsed, perhaps many others are still intact. The ancient relics of Mars's volcanic past. Now, after lying dormant for perhaps millions of years, these lava tubes could bring life back to the red planet. That life will be us. One of the challenges of living on Mars for future humans will be the radiation environment, and in particular, when there are solar storms. The cosmic rays coming in can be deadly. And having a storm shelter under some large mass of rock is really the best way to protect yourself from cosmic rays. On some planets, storms are impossible. Superheated Mercury is too small and too close to our sun to have a significant atmosphere. And no atmosphere means no storms. But move out, away from the sun, and we find worlds with turbulent, chaotic atmospheres. They can spawn some of the most awe-inspiring megastorms in our solar system. This is Venus, a planet completely shrouded with clouds. Winds rip around the upper atmosphere at over 300 miles per hour, about 35 miles above the surface. The winds are whipping around in a ferocious pattern that basically carries the cloud features around the entire planet every 4 days. Venus is closer to the sun than Earth, and it's heat from the sun that drives the wind. The circulation pattern of Venus's clouds is actually quite simple. There's a warm side of Venus and a cold side, and as air warms up and rises on the day side of Venus, it spreads around to the night side. So there's this continuous current. It's actually quite a lot simpler than the atmospheric circulation on Earth. Venus's winds circulate faster than the fastest hurricane on Earth. But they look very similar. The Venus Express probe captured these remarkable images of the planet's south pole. One of the great mysteries of Venus, which actually had jaws dropping in the halls of many astronomy departments, is the fact that we have hurricanes at the poles of Venus, especially in the southern hemisphere, that have 2 eyes. Not 1 eye, but 2 eyes. Now, we've never seen this before on such a planetary scale. Venus's double-eyed vortex is 1,800 miles wide. two hurricanes whirl around each other. If you could descend into the vortex of Venus, something I would love to do, at least with a remote machine, I think you would see some kind of a fantastic wall of cloud, and this sort of twisting form spinning around you at ferocious speeds. It would be quite a sight. It's a mystery how deep this raging, spinning vortex goes. But maybe this megastorm eye descends to the planet's surface. Down here, permanent twilight bathes a volcanic landscape, and the atmosphere's colossal weight creates immense pressure. And the atmospheric pressure on Venus is about 100 times that of the Earth. Think of taking a car, squeezing it down to about a square inch, and putting it on every square inch of your skin. You'd be flattened within a fraction of a second. Because of all that pressure, Venus's dense atmosphere creates one of the strangest megastorms imaginable. 4 mph winds with the force of a hurricane. The winds on the surface of Venus are actually very slow, because Venus has a very slow rotational rate. It takes Venus about 8 months to turn once around with respect to the Sun. The crushing atmospheric pressure rams gas molecules together so tightly that they feel more like a liquid. A gentle 4 miles per hour breeze packs a brutal punch. It's like a hurricane in slow motion. Winds on Venus are totally unlike anything we see on the planet Earth. It would almost feel like a molasses effect. It'd be quite difficult to simply walk and run right through the wind. Venus's surface is so hostile that life is impossible here. But the upper atmosphere's faster winds hold an extraordinary possibility. I harbor this, I don't know if I would call it a hypothesis or a scientific fantasy, but I do think it's plausible that there could be some kind of life living in the clouds of Venus. There are certainly energy sources, there's sunlight, and there are certainly nutrients. There's carbon, there's hydrogen, there's oxygen. All the stuff we think of that you need to make life exists in the clouds of Venus. Earth's atmosphere is full of life, microscopic bacteria drifting on the wind. Could Venus be the same? Perhaps one day we'll send a probe to find out. Leave Venus behind, and the next planet is Earth. Here too, the weather gets extreme. We are bombarded by tornadoes, hurricanes, and these dust storms. On Earth, they're localized. But on the next planet out, they engulf an entire world. Over 100 years ago, astronomers thought they had found life on Mars. A dark wave spread from the pole toward the equator. They thought it was springtime vegetation spreading across the planet. They were right about the season. Mars tilts at roughly 23 degrees, like the Earth. So you would have summer, fall, winter, spring, like the seasons. Seasons bring weather. The shadow astronomers saw was actually dark rocks uncovered by a violent dust storm. It's all because of the way the planet tilts. The Earth takes 1 year to orbit the Sun. In January, the northern hemisphere leans away from the Sun, and we get a winter. In June, it leans inwards, or summer. Mars has gigantic planetary dust storms, the like of which we've never seen here on the planet Earth. Mars has around the same tilt as Earth, and springtime means the storms. The Martian surface vanishes under a cloud of raging dust particles. On Earth, we get dust storms too. They can be devastating, swallowing entire cities. July 5th, 2011, Arizona. An unstoppable 5,000 feet high wall of dust smashes into Phoenix, Day turns to night. Thousands of tons of dust settle over the city, but the disaster stays in one place. Mars's dust storms can engulf the entire planet. On Mars, when dust gets kicked up, once it lands, it can get kicked up again and again. The dust is reusable. On the Earth, when dust gets kicked up and then finally settles out, it's probably going to settle out into the ocean, where it's gone for good. There's nowhere on Mars where there isn't ready dust and sand to add to that storm. So these storm systems can kick up and last weeks or even months. Mars's incredibly dry atmosphere contributes to the storm's size and power. In the case of the Earth, dust that gets up into the atmosphere is rapidly washed out by the rain and gets into the ocean. In the case of Mars, there's no comparable rain to wash the dust out. So once the dust gets into the atmosphere, it just sits there until the particles by themselves are able to slowly settle out. A lack of rain allows Mars's dust storms to cover the planet. But dust storms on Mars can be equally spectacular on a much smaller scale. NASA rovers captured these extraordinary images, dust devils sucking up fine, dry iron oxide dust. The biggest dust devils can reach 6 miles into the sky. They pump fine particles high into Mars's atmosphere, creating a haze of dust that may help control the planet's dry climate and lead to a planet-wide megastorm. Even on Mars, dust storms this big are rare. Astronomers have detected just 10 in the last 100 years. What the ancient astronomers mistook for life was a megastorm. But even a planet-covering dust storm is dwarfed by the weather on the next planet out from our sun. This is the giant of our solar system, Jupiter. Jupiter is gigantic. It's 2.5 times more massive than all the other planets in the solar system added together. It's also home to gigantic megastorms. Jupiter's high-speed rotation drives vast bands of counter-rotating clouds. Colossal storms build along the boundaries. And this is the biggest of them all, the oldest storm in the solar system. 15,000 miles across and over 300 years old, the Great Red Spot. Around the edges, turbulent winds rage at over 3,100 miles per hour. The Great Red Spot is a giant vortex, meaning that in the case of the red spot, it has a high-pressure center with winds that swirl around the outer edge. So in that sense, the Great Red Spot is a little bit like a hurricane. A hurricane with a difference. On Earth, hurricanes feed off heat from the ocean. When they hit land, they start to die. So, on average, they last only about a week. Jupiter does not have land. Jupiter is a completely gaseous planet. The friction there is very weak. And so, a vortex, like the Great Red Spot, can last indefinitely. There's nothing to slow it down. To keep going, all the red spot needs is a power source. On Earth, ultimately, that's heat from the sun. But Jupiter's 5 times farther from the sun than us. Heat from the sun is not enough to drive the red spot. Instead, Jupiter has an internal power source its own immense gravity. In 1995, NASA launched a probe straight toward the giant planet's heart. It plunged into Jupiter's upper atmosphere at over 106,000 miles per hour. As it fell, the planet's crushing gravity ratcheted up the pressure 10, 15, 20 times what we feel on Earth. Winds gusted to over 400 miles per hour. The probe gave out just 100 miles in, crushed by pressure and fried by the incredible heat. The pressure generated, had the probe made it deeper, it would have reached a vast silvery ocean. Intense pressures here turn hydrogen gas into a churning metallic liquid, superheated to over 40,000 degrees F. Jupiter's interior pumps out about twice as much energy as the surface gets from the sun. This is Jupiter's power source, the heat that drives its massive megastorms. All of the convection, all of the heat comes from the hot, dense interior of the planet itself. So the bands of clouds that you see, that are even counter-rotating, going in different directions, those are all driven by the internal heat of Jupiter itself. Jupiter's internal heat drives its violent megastorms. But the giant planet may hold clues to an even deeper mystery. Could life exist on other worlds? NASA's Cassini probe studied Jupiter as it flew past en route to Saturn. It made an extraordinary discovery. Strange white clouds just north of the Great Red Spot. Clouds just like the clouds on Earth. Droplets of liquid water. Could Jupiter have the ingredients for life? The question of life on the giant planets is an interesting one. You have many of the ingredients for life. You have sunlight coming in. There's liquid water, at least in the form of cloud droplets. On the other hand, if life can easily exist in clouds, you might expect that bacteria and algae would populate the clouds on Earth, and the clouds would be green. We don't see that on the Earth. We do see microbes at many altitudes throughout the Earth's atmosphere, but they seem to largely be blown off of the surface. It's likely that life on Earth began on a solid surface. But could life evolve without one? There's no surface on Jupiter. And so that makes it difficult for organisms to have a constant source of water. So if you imagine yourself being a little bacterium inside a cloud droplet, you're going to be in deep trouble when that cloud droplet evaporates. Whether life exists in Jupiter's clouds or not, gas giants like Jupiter and its neighbor Saturn have all the right ingredients: water, heat, and one other vital element, a spark. Lightning, on an unimaginable scale. These haunting images are from NASA's Cassini-Probites mission to explore one of the solar system's most awe-inspiring planets, Saturn. The probe reveals Saturn's rings, moons, and the planet itself in near perfect detail. Chaotic bands of cloud race around Saturn at more than 1,000 miles per hour. Finding storms here was no surprise. It's a planet of storms. But this was astonishing. A bolt of lightning, a gigantic thunderstorm on an alien world. Lightning creates some of the most spectacular weather on Earth. Electrical tension builds between the top and bottom of a vast 55,000 feet high storm cloud, a maelstrom of water vapor, rain, and ice. Tiny ice crystals drive up past hailstones falling down. As they rub past each other, it builds up a charge. When the strain gets too great, you get an electric spark. On Earth, the average lightning storm stretches 15 miles. On Saturn, they can reach around the whole planet. There are examples of lightning storms on Jupiter and Saturn, where the anvil cloud, in other words, the big cloud at the top of the storm, starts small and grows to be 20,000 kilometers long. That's the size of the Earth. Earth. On Saturn, we registered one lightning storm that was 10,000 times greater than any lightning storm found on the planet Earth. Lightning is hotter than the surface of the sun. The atmosphere literally explodes the sound we call thunder. On Earth, it's the sound of new life. Lightning seems scary and destructive, but actually, it's very productive for life on Earth. And the reason why is because of its influence on atmospheric chemistry. Every bolt literally burns the air. When you have a lightning discharge, you get this very high temperature, very energetic plasma, and that breaks up the nitrogen molecules in the atmosphere, frees up those nitrogen atoms to enter into other kinds of molecules. And those nitrates, formed by lightning, allow nitrogen to go into the soil as, basically, fertilizer, enter into plants, enter into the life cycle. So it's the lightning that frees up nitrogen atoms in the surface of life on Earth. Earth experiences 8 million lightning bolts every day, helping life evolve and colonize the planet. But for Saturn, lightning alone may not be enough. There's nowhere for alien life to live. One place in our solar system may solve that problem: Saturn's moon, Titan. It has an atmosphere. It has lakes of liquid methane, and its own bizarre brand of megastorm. Saturn is almost 900 million miles from the Sun. This far out, orbiting the Sun takes time. Saturn's year is nearly 30 Earth years long. Right now, it's spring, and things are heating up. Now, we're moving into the summer cycle of Saturn, so the atmosphere is slightly heating up. Even as distant as Saturn is from the Sun, we've got a little more energy. And we're seeing the most spectacular storms we've ever observed on Saturn. After years of frozen silence, Saturn is coming alive. Scientists have waited nearly 15 years for the Sun to light up its North Paleto, reveal extraordinary details about one of the strangest megastorms in the solar system, Saturn's unique hexagon storm. A hexagonal pattern. How can that be? In Mother Nature, we have jagged objects. We don't have geometric figures arranged precisely, especially at a gigantic planetary scale. However, there's some theories. If I take a bucket of water or a bathtub and simply vibrate it, I get waves that travel. But there's another kind of wave. You have traveling waves, but then you have stationary waves. Inside a bucket of water, you can get resonances. Water pulsates like this. And you can also get them to pulsate in a circle like this to create regular patterns. These are called stationary waves. And we think that this mysterious hexagonal pattern on Saturn is a hexagonal standing wave. The megastorm at Saturn's North Pole is a wind that travels at hurricane speed, cornering sharply 6 times as it races around the planet. The central clearing is so big, you could fit 4 Earths inside. What lies beneath its surface is a mystery. As Saturn warms from spring to summer, another world comes alive too. One of Saturn's moons, Titan, is warming up. And with the warmth come the storms. One of the most interesting moons in our solar system is Titan. It's straight out of science fiction. It's an object with yellow skies and methane clouds that is truly remarkable. NASA's Cassini probe reveals Titan in unprecedented detail. Thick, dense atmosphere, vast mountain ranges, lakes of liquid methane, and this. An arrow-shaped band of white methane clouds moving over its surface. When the clouds drifted over a dusty, open plain, seen here as a dark patch, the dark patch ground beneath the clouds grew larger. Scientists believe liquid methane drenched the surface. a spring rainstorm, Titan style. Rain on Titan, if it exists, would be very different from rain on the planet Earth. First of all, the gravitational field is very weak. So you would actually see raindrops falling very slowly at you. Also, the size of these droplets could be much larger. But don't get caught in a rainstorm on Titan. Those droplets are awfully cold. Titan's methane monsoon sweeps across the moon. Weak gravity creates ultra-cold, hazelnut-sized raindrops, an alien world with truly alien weather. These slow drops have carved valleys and lakes, much like ours on Earth, a slow-motion megastorm. But fly even farther out through the solar system, and you find storms that are altogether faster. This is super chilled Neptune. The temperature never gets above 300 degrees below zero. Neptune is one of these giant planets. It's much larger than the Earth and has a very thick atmosphere. It's about 2 billion miles out from the Sun. So you really might expect, since it's that far from the Sun, it would be very cold and not have very much weather. But in fact, Neptune is very dynamic. It's got tremendous weather patterns. Despite its incredible distance from Earth, astronomers can get close to Neptune's turbulent atmosphere with a little help from this. The Keck Observatory, 14,000 foot up on the summit of Mauna Kea in Hawaii. It sits above Earth's clouds and pollution. The telescopes are so powerful, they could see a candle on the moon. Neptune at first appears featureless, but a closer look reveals white, high-altitude clouds in the upper atmosphere. It's a perfect opportunity to track wind speed. Measuring the time and distance the clouds take between 2 points allows scientists to clock their speed. The Keck telescope swings towards Neptune. A series of shots track the white clouds as they move around the planet. So here, we can take several photographs that show the positions of clouds apparently changing. You can measure the position at one moment to be there, and at another time, a few hours later, to be in a different place. Now, most of that change in position is due to the rotation of the planet as a whole. However, if you know the rotation rate and subtract that out, that gives you the motion of the clouds relative to the planet. That tells you the wind speed. The results are shocking. We're seeing wind speeds on Neptune of many hundreds of miles an hour, up to 1,200 or even 1,260 miles per hour for the very fastest clouds. That's really phenomenal. Neptune has the fastest winds in the solar system. So what's driving this? You need energy to make weather. Where's that energy coming from? And it turns out it's coming from Neptune itself. It does receive sunlight. But Neptune actually radiates away more energy, a lot more energy, than it gets from the Sun. Which means the interior is very hot. Probably, it means there's radioactive material in there. There's leftover heat from when Neptune formed 4.5 billion years ago. That's very slowly leaking out. And it's that that's heating up the air and driving all of the circulation and all this crazy weather that Neptune has. Neptune's storms hit hard. The search for truly extreme weather takes us out of the solar system altogether into uncharted territory. Out here, there are storms that make even Neptune's winds look like a breeze. Katrina was just a sneeze compared to the winds we have on Osiris. The search for megastorms leads to alien worlds whose violence defies imagination. space is full of stars and planets, where violence and chaos reign. Astronomers scour the skies for new worlds, and the king of the planet hunters is Professor Jeff Marcy. He scans the night sky, seeking new worlds around distant stars. Marcy's team has instruments so sensitive they can even predict the weather on these distant planets. This is Osiris, 150 light years from Earth. A planet from hell with matching weather. Earth is 93 million miles from the sun. It orbits the sun in 1 year. But Osiris is just 4 million miles from its star. Its year races by in just 3.5 days. When Osiris passes between us and its star, starlight briefly shines through its atmosphere, giving us a glimpse of conditions on the alien world. And they waited until the planet was in front of the star. At that moment, some of the starlight passed through the atmosphere of the planet. They were able to do, essentially, a chemical assessment of the composition of this atmosphere. Osiris gets blasted by the intense heat of its star. Temperatures top 2,000 degrees. Now, what that means is that the environment on that planet is, well, hideous for life as we know it. But even more, the intense heat causes the gases to expand, and they have no place to go but the backside of the planet. Osiris is tidally locked. The same side of the planet always faces the star. The other looks out into space. The temperature difference is immense. Superheated atmosphere roars from the bright side of the planet to the dark at nearly 6 times the speed of sound. In fact, the winds will be something like 2,000 or 3,000 miles an hour. Enormous speeds of these winds, 10 times, 20 times faster wind speeds than the strongest hurricanes. Katrina was just a sneeze compared to the winds we have on Osiris. Osiris is a brutal world, too hot and too violent for any kind of life we could imagine. But there are even larger megastorms. Storms on the scale of whole galaxies. And these fast storms may be the reason any of us are here. The Hubble Space Telescope captured this stunning image of the galaxy NGC 3079. At its center, a superwind storm on a truly cosmic scale. It was triggered by an explosion from a forming star. This raging galactic storm is about 3,000 light-years wide. It has already raged for around 1 million years. Filaments of 20 million degree gas tower above the spiral galaxy. This cosmic megastorm wreaks havoc within its host galaxy. We see bubbles and jets and formations of gas falling into the galaxy, colliding with galactic dust. The gas from the galactic megastorm smashes into gas and dust at the heart of the galaxy and compresses it into a swirling mass of matter. Gravity takes over. The compressed clouds of gas and dust get tighter and tighter. The center gets hotter and hotter. Finally, it ignites. Powerful winds from the new star blast into space. The whole cycle begins over again, and a new galactic megastorm is born. Around the fledgling stars, dust and rock come together. The birth of new worlds with rocky surfaces where life could begin. And perhaps the formation of life itself may be determined by how these gases swirl and create supergalactic storms. And if you have galactic winds turning away, then that would help to distribute the elements necessary for life throughout the galaxy. So galactic storms may, in some sense, be one clue to the formation of life itself. Galactic megastorms rage for millions of years. billions of years ago, they may have created new homes for life in our Milky Way galaxy. On every scale, storms are not just a force of destruction. They are linked to creation itself. The search for life on other worlds is also the search for storms. When you disrupt the status quo, you open all kinds of possibilities for things to reassemble in different ways. So chaos, or disruption, is actually an important factor in the development of complex systems like life. A planet that might have changes of seasons, volcanism, intense storms, environmental factors that you might think could be damaging to life in the long run makes life stronger. The Earth a giant mass of rock and water flying through space. It's unlike any other planet we know because it supports life. It's not just our home. It's the only safe haven we have in the universe. But how did it get here? What strange forces of nature created this living, breathing planet we depend on? It's a mystery scientists are only now beginning to solve. Naked science brings together the latest research to discover just what it took to create an Earth on which people could live. In this vast cosmos, there's only one place we know where humans can survive. It seems as if the Earth was made for us. It supplies us with water to drink, food to eat, and air to breathe. It's the only home we have, and we rely on it entirely. But 5 billion years ago, it did not exist. Where the Earth now sits in the outer reaches of the Milky Way galaxy, it was just a large cloud of gas and dust. This is the astonishing story of what transformed that cloud of dust into the planet we know today. One person who understands what it takes to build a planet is astronomer Tom Fleming. Using telescopes like these at Kidd Peak in southern Arizona, astronomers have pieced together how the Earth was born. It all begins with a big cloud of gas and dust. Little particles of dirty stuff grains of sand, grains of silicon. Scientists call these regions of dust and gas, molecular clouds. But they're not like any clouds we see on Earth. Molecular clouds are vast. They cover hundreds of light years in size. It was from clouds like these, photographed by the Hubble Space Telescope, that the Earth formed. The clouds are made up from the debris of hundreds of dead stars. When stars from the early years of the universe burned up their fuel, they exploded and showered the surrounding space with their ashes. When the first generation of stars died, either gently or explosively, in an event we call a supernova, the heavier elements, the irons, the silicons, aluminum, nickel, that was created in the star is blown out back into the galaxy. This cocktail of elements creates a molecular cloud. From this, new stars are born and planets. The force that drives their creation is gravity. The same force that attracts apples to Earth will attract two objects in space toward each other. It draws the dust particles of the molecular cloud together. Over the next 10 million years, the molecular cloud slowly contracts under the force of its own gravity. As our gas cloud collapses under the force of gravity to become a star, something very interesting happens. And I'm going to try and demonstrate what happens with these two lead balls and this carousel. Now I'll step up here on top of the carousel. I've now increased my mass by the mass of two lead balls, and I'm holding them straight out. So now, the mass in my body is distributed at a distance far from the center. Fleming is impersonating a molecular cloud. The weights represent its mass, which, to start with, is spread over a huge area. Now I'm going to ask Lucy to give me a hand here and give me a little bit of angular momentum. As I start spinning, I'm going to move the balls closer to the center of my mass and notice how faster I'm spinning. And when I bring them out, I slow down again. And as you can see, this is exactly what happens to the interstellar cloud. The large molecular cloud has had a small rotation. When it shrank, this rotation speeded up. As the cloud contracted, the energy of the material flying in from space caused its center to heat up. This spinning ball became our sun. The rest of the cloud was spinning so fast that it spread out into a vast disk of dust and gas. This was the cradle of life, the material that would form the Earth and all the other planets. Until recently, what turned this dust into a planet was a mystery. Then, in March 2003, a light-hearted experiment on board the International Space Station led to a significant discovery. Astronaut Don Pettit was curious to see the effects of weightlessness on different substances. In a series of simple experiments, he filmed bubbles, indigestion tablets, swirls of colored water, then filled a plastic bag with salt. This last experiment turned out to be a scientific revelation. But at the time, Pettit didn't realize its significance. The person who worked out what it meant was fellow astronaut Stanley Love. Don likes to mess with things. And one of the things he messed with was putting things in plastic bags, granular solids like sugar, salt, instant coffee. He put them in a bag, inflated the bag, and shook them up, just to see what would happen. And what happened was the little particles formed up into clumps, like dust bunnies, instantly. When he saw a video of the experiment, Love realized that he was witnessing a significant discovery. And Don shot this video down. He said, "This is cool. Isn't this neat?" And showed all his little videos and his different substances and the different bags. And I said, "Don, yeah, that is neat. Actually, you've solved a very old problem in planet formation. In zero gravity, the crystals behaved completely differently to the way they behave on Earth." Love recognized what was making them stick together. Well, anytime two different materials rub together, you can have a few electrons get traded off from one material to another. This happens when you rub a rubber balloon on your hair and stick it to the wall. As it turns out, once you get dust, or basically anything, in zero gravity, and shake it up, let it bump into each other, we think it gets some sort of electrostatic charge on it, which makes it clump up together just immediately. You can break up the clumps by shaking the bag up, and then they reform as soon as you stop shaking it. In the first few seconds of its life, our Earth may have looked something like this. Scientists think that this moment occurred 4.5 billion years ago. To follow the evolution of our planet, naked science is going to represent the time from then to the present as 12 hours on the face of a clock. At noon, the clock started ticking. The Earth's journey, the journey toward becoming a planet that can support life, has begun. The first step didn't take long. Once clumps of these particles had grown into objects about 1/2 mile in diameter. Their mass was great enough for their gravitational pull to attract material from the surrounding disk. Like giant vacuum cleaners, they circled the sun, sucking in material from the disk until there was nothing left to consume. In the inner solar system, these clumps grew into around 20 planets. This process took about 3 million years less than 30 seconds on our clock. The next stage of the Earth's evolution was incredibly violent. As these 20 planets orbited the sun, their gravity affected each other, and they began to collide. With each collision, 2 planets combined. Over time, these collisions reduced the inner solar system to just a few planets, including Venus, Mercury, Mars, and Earth. Astronomers believe that the Earth grew to this stage in around 30 million years. We are now just 5 minutes into our story. But what was early Earth like? What would happen if a human had landed here? The energy from the collisions with other planets made the Earth incredibly hot. At around 8,200 degrees Fahrenheit, its temperature is more than 5 times that inside a cremation furnace. A human would almost instantly disappear in a puff of steam and ash. But even as our planet cools down, another danger threatens. A storm of charged particles is approaching the young Earth. It's so intense that it could end all chance of life. 4.5 billion years ago, a giant cloud of dust collapsed to form our solar system, the Sun, planets, and Earth. But as the newly formed Earth began to cool, it faced one of the biggest threats to its existence, a hurricane of deadly particles from the Sun. Boulder, Colorado. At the Space Environment Center, meteorologists monitor the storms on the Sun. It's the most extreme weather you're likely to see. A light breeze out there is at 200 miles per hour, and the low temperature is 8,000 degrees Fahrenheit. Around-the-clock surveillance is necessary, because storms on the Sun affect us here on Earth. Space scientist Rodney Virek knows just how deadly the Sun can be. The Sun is a large explosion, and from that explosion, energetic particles are released. These particles make up the solar wind, and they travel toward Earth at speeds of up to 1 million miles an hour. If the solar wind becomes too strong, it can kill. We watch the Sun, and when we see something that may produce energetic particle events here at Earth, we try and warn Astronaut 7 Airlines about these types of events. The charged particles in a solar wind are a form of radiation that can cause lethal damage to living cells. An intense solar storm could kill an astronaut caught in space. But the solar wind can also have a devastating effect on planets. The Earth is surrounded by an atmosphere, a thin layer of gases that protects it from the extreme temperatures of outer space. But when charged particles in the solar wind hit a planet's atmosphere, they can strip it away. You can see how destructive the wind can be by looking at Mars. Over millions of years, the solar wind has blown away most of its atmosphere. Now there is no liquid water on the surface, too little air to breathe. This could have been the fate of the Earth. So why wasn't it? The answer lies in the moment of the Earth's creation. As the early Earth was forming, the energy released as material hit the planet produced heat. The heat became so intense that even rock melted. The lightest elements in the molten Earth rose to the surface, while the heaviest elements, including iron, sank down toward the center. Here, they formed a molten core. It's this iron core that protects us from the deadly effects of the sun's rays. Exactly how the Earth's core protects us is a mystery that drives the research of Dan Lathrop. In his laboratory at the University of Maryland, he spins scale models of the core to study how it behaves. The Earth's core has dynamo action that makes a magnetic field. And that's a process where currents in the liquid iron cause magnetic fields. Lathrop has found that the spinning motion of the core creates a magnetic shield that surrounds the Earth. You can see it's mostly axisymmetric, but you're getting small details that are rotating around with the inner sphere. To show how it does this, Lathrop has rigged up a simple high school experiment. We can see how the currents produce magnetic fields with this simple demo. Just take some iron filings and sprinkle them down around this coil of wire. This coil of wire represents the core of the Earth. The iron filings will reveal the shape of any magnetic field. And then hook the coil up to a power supply. You can see the iron filings line up with the magnetic field lines, and the magnetic field lines are passing through the center of the coil and looping around the ends. The electricity in the coil produces a magnetic field. The same thing happens on a larger scale with the Earth's core. This magnetic field gives our planet its north and south poles. It also extends far out into space. It's called the magnetosphere, and this is what protects us from the solar wind. As particles from the sun fly toward the Earth, the magnetosphere blocks their path. Those that get through are deflected toward the poles. Here, as they enter the Earth's atmosphere, they react with molecules in the air to create the aurora, the northern and southern lights. Today, the solar wind still erodes our atmosphere, but thanks to the magnetosphere, the loss is not life-threatening. It's been estimated that between 5 and 10 pounds a second of our atmosphere are dragged out into the solar wind. Fortunately for us, even at that rate, the amount of time it would take to deplete our atmosphere would be many times the life of the sun. The magnetic field produced by the iron in the center of the Earth played a vital role in our planet's evolution. Without it, we wouldn't have any air to breathe. On our clock, in which 12 hours represents the whole history of the Earth, just 6 minutes have passed. The Earth still doesn't look like the planet we know. But could a human now survive on its surface? It's possible that the Earth may have cooled enough for a human to survive in a heat-resistant suit. And thanks to its iron core, our planet is now protected from the solar wind. But there is still no oxygen or water on Earth. We wouldn't last a minute. Worse still, if a human could survive, they would be in for a shock. An astonishing event is about to take place. The Earth is on a collision course with another planet and about to experience the biggest bang in its history. So far, we've seen how a giant cloud of gas and dust collapsed to form our solar system, and how the Earth's molten iron core created a magnetic field that protected the planet from the deadly effects of the solar wind. The Earth's formation was a violent and dramatic process. But an even more astonishing event was about to take place, a collision so large that it would melt the whole planet. And the only reason we know this event happened is thanks to a large object circling over our heads. The moon is the Earth's constant companion. For centuries, humans wondered where it came from. There were many theories. Some thought that it was formed by the early Earth spinning so fast that it threw off material into space. Others proposed that the moon was a passing planet captured by the Earth's gravity. But no one really knew. Minutes to start. In 1963, the United States launched the Apollo program. One of the mission's aims was to discover how the moon was formed. Houston, Sweet 16 has arrived. Okay, you're go for landing. Okay, down at 3. Stand by for contact. Contact. Wow, fantastic. In the late 1960s and early 70s, American astronauts made 6 visits to the moon. They played golf, tested their skills at off-road driving, and collected 840 pounds of moon rock for scientists back home to study. How about rolling that one over? No way. The pieces they brought back to Earth revealed something strange. When scientists examined them, they found that they were very dry, as if they had been heated. This was baffling. Any theory of the moon's creation needed to explain this mystery. In the 1990s, planetary scientist Robin Canup decided to put a new theory to the test. Using a supercomputer simulation, she modeled what would happen if the Earth collided with another planet. The results were a revelation. This is a simulation of a single impact by a roughly Mars-sized planet, she explains, shown here on the upper right, colliding with the young proto-Earth, represented by this object here. So the impactor comes in and hits the Earth at a very oblique angle, at about 45 degrees. And you can see this long arm of material right here. That's actually the impactor. It's been stretched out and distorted by the impact event itself. There's an inner clump of material. You can see it right here that will re-impact with the Earth after a little more time. This outer clump of impactor material makes a very close pass by the Earth. As a result of the Earth's gravity, this initial clump is sheared out into a long arm of material, which then finally breaks up to form a disk. And it's from this disk of material orbiting the Earth that we believe the moon then later accumulates. From this simulation, Canup has figured out exactly what happened during the impact. There would have been this unbelievably large impacting planet racing towards the Earth at a speed of 7 miles per second. This would have been an enormous object, a planet, that was half the size of the Earth itself, and so would have completely filled the sky just before impact. The impact itself was an incredibly energetic event, with enough energy to completely melt the whole of the Earth and vaporize a significant portion of the rock in the Earth. When the planet hit the Earth, the glancing blow smashed material into space. Much of this debris stayed in orbit as a vast disk of rock and dust. A clump of this circling material then became large enough for its gravity to suck in other matter from the disk, and this became our moon. It's now 50 million years since the Earth began to form. On our clock, in which 12 hours represents the whole of Earth history, still only 8 minutes have passed. At this stage in its life, the Earth appeared very different from the planet we know. The ground remained molten from the impact for thousands of years. And the moon was 15 times closer than it is today. You can imagine what is now a stunning sight on a full moon night would have been breathtaking at that time, with the moon 15 times larger than we currently see it. The collision with the planet and the formation of the moon were key events in creating an Earth fit for life. The collision could have tilted the Earth on its axis. This tilt gives us the seasons. Laughter. Thanks to this tilt, the Earth's climate changes gently through the year. It gives us the annual cycle of life. It may have been possible for life to evolve on Earth without these seasons, but it would have been a very different planet from the one we know today. The creation of the moon also gave us the tides. When the moon was close, these were much stronger. But they have weakened as the moon has slowly drifted away. Nowadays, we take the oceans for granted. But 4.5 billion years ago, they didn't exist. And without water, there could be no life. Where all our water came from and how it got here is one of the most amazing stories in science. Naked science is investigating the birth of the Earth. How did nature build a planet on which humans could live? So far, we've seen that the Earth formed from a giant cloud of gas and dust. Its iron core created a magnetic field that protected it from the deadly particles of the solar wind. And it survived a big hit from another planet. But for the Earth to have life, it had to have water. Where that came from is one of the great mysteries of science. There are currently around 326 million trillion gallons of water on the planet. That's 394 trillion Olympic swimming pools. But many astronomers think that if the early Earth contained water at all, it had very little. At the time the Earth was forming, the inner solar system was too hot for liquid water to exist. The region from the Sun to the asteroid belt was almost bone dry. The nearest water reserves to the Earth were now 160 million miles away in the outer asteroid belt. Out here, far from the Sun's heat, water froze and was incorporated into the forming planets and other objects. But how the water could have traveled from here to the Earth is a mystery scientists are only just beginning to solve. One clue came with the blastoff in January 2005 of an unusual NASA spacecraft named Deep Impact. Its mission was to fly 270 million miles to a comet named Tempel 1 and launch an 800 pounds copper impactor into its surface. The mission was the latest attempt to understand some of the most mysterious objects in our solar system. For centuries, people had argued that comets had brought water to Earth. When they looked at the moon, it was clear from the craters that its surface had been bombarded by large objects. Similar objects must also have hit the Earth, although our planet's much more dynamic geological activity has since erased all trace of them. Scientists also felt certain that comets contained water in the form of ice. But the Deep Impact mission was the first time anyone had probed inside one. On the morning of July 4th, 2005, NASA scientists watched anxiously as the impactor approached the comet at a speed of 23,000 miles per hour. It scored a direct hit. The explosion was captured by telescopes around the world. Analysis of the debris confirmed that comets contain significant amounts of water. But could they have brought that water to Earth? Using radio telescopes, astronomers have studied the type of water in the vapor trails of comets. They wanted to know if it matched the water on Earth. So far, scientists have only analyzed 3 comets, but the results are not encouraging for the comet theory. The water in all these comets was not the same as the water in our oceans. The comet theory isn't yet dead, but it's fizzling out of steam. In its place, scientists have evolved an exciting new idea. A vital clue arrived on January 18, 2000. That evening, the sky above Western Canada lit up with a bright light. Dozens of witnesses saw a meteorite enter the Earth's atmosphere. Seconds after the event, local photographers took these pictures of the trail it left in the sky. As it fell to Earth, the meteor broke up into dozens of pieces and landed on Tagish Lake in British Columbia. Within days, scientists were on the scene extracting the frozen remains. The pieces they pulled from the ice were the best preserved meteorites ever recovered. Still intact, a piece was shipped to NASA's laboratories at the Johnson Space Center in Houston. Here, space scientist Michael Zelensky examined it. The meteorite was remarkably undamaged, despite heating up through friction as it entered the Earth's atmosphere. The meteorites, they're cold-soaked in space for millions of years, so they're very, very cold. And the air in the atmosphere at high velocity, they do, in fact, get very hot on the outside. But they're only heated for a few seconds, and that's not long enough for the heat to get all the way in past a few millimeters, actually. This means that when meteorites hit the ground, they cool very quickly. You hear of reports of meteorites causing fires on the ground, things like that. That's always wrong. They're actually quite cold to the touch after a few seconds. But when a meteorite is fragile, like the one at Tagish Lake, where it lands makes all the difference. Very lucky it fell in a frozen lake. If it had fallen anywhere else, it would have easily fallen apart to dust in a few days. And so it's quite possible this kind of meteorite falls to Earth very, very commonly. It's just usually destroyed. Because the inside of the meteorite remained frozen, Zelensky was able to analyze what it was made of. This is a sample of the Tagish Lake meteorite. The black material here is mostly clay minerals, the kind you'd find in your yard. And these clay minerals contain water molecules trapped inside. And so, about 20% of this meteorite by weight is water. That's a huge amount. From the location and angle at which the meteorite fell, astronomers traced its orbit back into space. They discovered that it came from the outreaches of the asteroid belt. If you do telescopic observations of asteroids, what you find is, as you move farther and farther from the sun, the asteroids have more and more water. Now, astronomers suspect that asteroids from this outer part of the belt brought water to Earth. If they're right, our oceans came from space in a torrential shower of meteorites. But one question remains. What could have caused so many asteroids to swing out of their orbit and come crashing to Earth? The culprit appears to be the biggest planet in the solar system, Jupiter. Jupiter lies just beyond the asteroid belt, and its mass is so great that its gravity disrupts the path of any object that comes near. In the distant past, it pulled thousands of asteroids out of their normal circular orbits into elliptical orbits that crossed the path of the Earth. When that happened, collisions were inevitable. The Earth was bombarded. As the asteroids crashed to Earth, they smashed apart. Water inside them escaped. Explosion by explosion, they created the oceans we see today. Scientists used to think it took hundreds of millions of years for the Earth to acquire its water. But recent evidence suggests it arrived remarkably quickly. The evidence comes from research carried out by geologist Stephen Mose in his laboratory in Boulder, Colorado. Mose took some of the oldest rocks in the world and ground them down. From inside them, he extracted tiny crystals called zircons. A zircon is a common mineral. It's generally small. It's hard to destroy. Using an ion microprobe, Mose then analyzed the zircons and measured the composition of the oxygen inside them. He found that the crystals had formed from a particular type of rock, one that could only have existed if there was water on Earth. What was startling, exciting, fun, was that these zircons showed not only that things on the Earth's surface had stabilized to within normal conditions, but that water was present. And water was present everywhere. Mose estimated the time the Earth acquired its water from the age of the zircons. The zircons in some of the rocks there are very close to 4.4 billion years old. This evidence suggests that the Earth's water arrived in less than 15 million years. On our clock, on which 12 hours represents the whole history of the Earth, that's just 25 minutes after the planet began to form. At this time, our Earth would certainly have looked very different. The sea was full of iron, much of it brought up from below by hydrothermal vents. And the atmosphere was a lot thicker than it is today. An ocean rich in iron would have appeared green. A denser atmosphere would have given a reddish tinge to the sky. Conditions for human existence are looking better. The land has now cooled to a tolerable temperature, and there is water to sustain life. But there is still one horrendous problem. The gases in the atmosphere are mainly nitrogen, carbon dioxide, and methane. There's not a lungful of oxygen in sight. Without oxygen to breathe, there's no way a human could survive. In early years of its life, the Earth experienced a violent and tempestuous onslaught. In time, the activity slowed until 500 million years after it began to form, the Earth had cooled and was covered in oceans. But there was still no oxygen in the atmosphere. Without that, animals and humans could not exist. One scientist who has investigated how the Earth acquired its oxygen is geologist Martin van Kranendonk. His research has brought him to Shark Bay on the west coast of Australia. It's a World Heritage Site, home to vast meadows with seagrass, dugongs, and tame dolphins. But Van Kranendonk has come to visit much older living things. This is one of only 2 places in the world where these strange living structures, called stromatolites, are known to exist. These stromatolites have been growing here since the end of the last ice age, about 10,000 years ago. And at that time, the sea level was a little bit higher, and so these structures grew up to the present height that you see them. Stromatolites are primitive structures. They come in 2 forms: short pillars of living bacteria and silt, and flat bacterial mats. The living part of the stromatolite is made up of blue-green bacteria that grow using photosynthesis. They take energy from the sun and convert carbon dioxide into oxygen. It's really the result of this process of giving off oxygen that we have planet Earth as we know it today, and habitats that people like us, humans, and all the other animals and plants are able to live on planet Earth. What makes Van Kranendonk believe that stromatolites created the Earth's oxygen is a remarkable discovery 1,000 miles away in a remote region of North Australia. This is the Pilbara, one of the oldest landscapes in the world. If you want to find out what happened early in the Earth's history, this is the place to come. It was really like you were transported back into a time machine of early Earth. It just sort of gave me goosebumps and shivers to walk over this ancient environment, where you could still see the processes that happened 3.2 billion years ago. Here, at a location kept secrets to preserve them, lie the oldest fossils ever discovered, the ancestors of the stromatolites in Shark Bay. What's remarkable about this outcrop in the Pilbara is that it contains the oldest evidence for life on Earth. We're looking at, here in front of me, our great-grandfathers and grandmothers. No one knows how life on Earth began, but these amazing fossils suggest that it emerged very soon after the planet formed. These fossil stromatolites are 15 times older than the dinosaurs. The bacteria that made them were living here just 1 billion years after the birth of the Earth. On our 12-hour clock, the time is now 20 minutes to 3. These would have been the first organisms that would have started the process of change of Earth's atmosphere to an oxygen-rich atmosphere, which has allowed us, mankind, and all the rest of life that we know today to evolve on planet Earth. If stromatolites existed on the Earth 3.2 billion years ago, they should have started to increase the amount of oxygen in the air. But it appears that they didn't. For the next billion years, the oxygen level in the atmosphere hardly changed. What happened to all the oxygen the stromatolites produced can be seen 300 miles away in this gorge in Australia's Karijini National Park. Hidden in these rocks lies the key to the mystery of the missing oxygen. Geologists call these rocks banded iron formations, and they believe that they owe their existence to stromatolites. Well, these banded iron formations are the product of a remarkable set of circumstances in Earth's history. They formed about 2.5 billion years ago, when the Earth was very young, and are the product, we think now, of microbial action in the ancient oceans. The Earth's early oceans were full of iron. As the bacteria in stromatolites bubbled out oxygen, it reacted with the iron in the water. You can see what happened in this simple experiment. This flask of water contains iron. It's the same color as the early oceans on Earth. This pump does the work of a stromatolite, pumping out oxygen. As the oxygen bubbles through the water, it reacts with the iron to form iron oxide, and it precipitates out as rust. There was so much iron in the oceans that for over 1 billion years, it absorbed nearly all the oxygen that the stromatolites produced. As the rust precipitated out, it fell to the bottom of the ocean and was turned into rock. It has been estimated that, around the world, these rocks have locked inside them more than 20 times the amount of oxygen that is in the atmosphere today. And they took an incredibly long time to form. On our clock, in which the whole history of the Earth is represented as 12 hours, we can see that the planet forms in the first 8 minutes. After 25 minutes, it has cooled and collected water on its surface. But it takes another 4.5 hours to remove most of the iron from the oceans and deposit it in these rocks. Only then does the oxygen level in the atmosphere start to increase. This happened approximately 2.2 billion years ago. And for the next 2 billion years, the level rose until, just 500 million years ago, it reached the level at which animals could survive. So, is our planet finally fit for human life? By this time, it has certainly cooled. There's water to drink and air to breathe. If we could travel back to this time, we could certainly survive. In our story, 11 hours have now passed. But the Earth still has a long way to go before the first human will walk on its surface. At 37 minutes to midnight, dinosaurs will emerge. At 10 minutes to midnight, they will be wiped out by a catastrophe. Finally, at 19 seconds to midnight, the first humans will appear. It has taken over 4 billion years, but out of a vast reach of freezing dust and gas, the forces of nature have created the only safe haven we have in the universe, our home, the Earth. For 5 billion years, an icy juggernaut had roamed the back streets of the solar system, flaring only as it swept close to the heat of the sun. But Comet Shoemaker-Levy number 9 hadn't reckoned on the mighty power of the planet Jupiter. Jupiter, king of the planets, destroyer of comets. The broken fragments of Shoemaker-Levy were big enough to remodel life on Earth. Each was being sucked in by the largest planet in the solar system. Each of their fiery descents was another chance to find out what it's really like on Jupiter. The most amazing thing about Jupiter, for us Earthlings, is that there's no place to stand. We see clouds. We see nothing but clouds. We don't see the ground because there is no ground. If I could take a spacecraft and fly through the upper parts of the atmosphere, there'd be swirls, there'd be powerful thunderstorms. I personally wouldn't take an airplane and fly into a hurricane. Well, the hurricanes on Jupiter are the size of the Earth. They're so powerful. Some people call Jupiter a failed star. Other people say, no, it's a very successful planet. If Jupiter was maybe 30 times more massive, the heat in the center would be so intense that nuclear reactions could start, and it would be like a second sun in the solar system. Long after the shock waves from Comet Shoemaker-Levy 9 had dissipated in Jupiter's stormy skies, the impacts were still being felt on Earth. We'd been jolted by a powerful reminder that the solar system can be a very dangerous place to live. No one is more aware of Earth's vulnerability in the cosmic shooting gallery than Gene Shoemaker, one of the comet's discoverers. He began carving out his scientific career here at Arizona's Meteor Crater in the 1950s. I've been studying craters all these years, so I've sort of had a fantasy. Wouldn't it be fun to actually see an impact? I sort of had in mind something that would land in the middle of the outback of Australia, where no one would be hurt. Small thing, and make a small crater, and we'd rush over and map it. I never dreamt about actually being able to witness an impact on another planet. But I was thrilled. You know, we're going to see an impact. Carolyn's reaction was, oh no, not my comet. Carolyn and Gene Shoemaker have scoured the world, chronicling a pockmarked history of planet Earth. As a team, they're formidable, having now discovered more impact sites on Earth and more comets in space than anyone in history. In fact, right over there, you can see where it's turned up, peeled up, and passes right out into the debris. So that's the hinge line right over there. It's such a thrill to actually discover something that probably no one else has ever seen before, and to find a comet that was going to actually hit a planet, an event that we could actually see. That sort of left us all just thrilled. We had a real high, and we knew that we were going to learn things that we would never have a chance to learn otherwise. For millennia, the bright beacon of Jupiter has caught the human gaze as it has traveled the heavens. But we had to wait for the invention of the telescope and a Renaissance Italian, a planet to begin giving up its secrets. On the night of January 7th, 1610, Galileo Galilei made a discovery that was to challenge Earth's claim to sovereignty of the solar system. Focusing his telescope on Jupiter, Galileo saw bright points of light in close attendance, little stars that shifted position. The logic was inescapable. Jupiter had at least 4 moons of its own. Io, a festering boil of sulfur and rock. Europa, with a silver surface of pure ice. Ganymede, a world of grooves and frozen slush. And Callisto, with its catalogue of craters. Here, circling mighty Jupiter, is an entire planetary system in miniature. Jupiter's dominance of the solar system is complete. 1,300 times the size of the Earth. It's a world so enormous, it could swallow every planet and moon in the solar system and still have room to spare. Looking back from Jupiter, the Earth is a feeble speck, circling a faint and distant sun. Today, the descendants of Galileo's telescope populate mountaintops around the world, and his dreams inspire a new generation of astronomers. What we see in the sky is the same thing that Galileo saw. And the reasons that we look, the reasons astronomers look in the sky, are the same reasons that Galileo looked. He was trying to find out what was happening out there. This same quest also set amateur astronomer David Levy on the path to Comet's discovery and his eventual meeting with the Shoemakers. I've been fascinated with Jupiter since the summer of 1960. That summer, I had my first telescope. And with my parents, I went outside, set it up, and looked up at the sky. And saw the brightest star in the whole sky saw. It had 4 little moons and little bands across it. And I said, "Hey, that's Jupiter." It's the first thing I ever looked at through a telescope. And I think if, that particular night, my dad had said, in 35 years from now, a comet with your name on it is going to go smashing into that planet, I would have been pretty surprised. If 4 centuries ago, someone had told Galileo that a spacecraft bearing his name was going to follow in the comet's footsteps, he too would have been quite surprised. On the 7th of December, 1995, Galileo, in name and spirit, reached out to touch the turbulent heart of Jupiter itself. Galileo, the spacecraft, is 3 tons of rocket and robot that will spend at least 2 years in the court of the king of the planet, locked in orbit as Jupiter's first artificial satellite. The spacecraft first took shape in the early 1980s at the Jet Propulsion Laboratory in Pasadena. It was a team effort. The main sections came from JPL and NASA's Ames Research Center The rocket motor came from Germany, and the fine wire mesh of the main antenna had to be spun by a stocking factory. The end result: the largest and most ambitious unmanned planetary explorer NASA has ever put together. In overall mission command, JPL's Bill O'Neill. It's a total commitment to the team at large. We are going to make this work. So we're going to do just a bang-up job on the Jupiter system. We're going to assault the Jupiter system with the most fantastic array of instrumentation you'd want to imagine. NASA has assaulted the Jupiter system before. Back in 1979, 2 unmanned Voyager spacecraft made the long haul to Jupiter and its 16 moons. As they passed through this Jovian kingdom, they encountered a realm of alien worlds, the like of which we had never expected. Here were the 4 large moons of Galileo, in close-up, the cracked shell of Europa, the strange grooved surface of Ganymede, heavily cratered Callisto, and the volcanic landscape of Io. These images left a powerful impression. I can't get Io out of my mind. It was one of the first things we saw. We saw many beautiful things after that, but it was so unexpected. Nobody had thought of any place having active volcanism on it, other than the Earth. It was a feeling of almost seeing a new world every day when we were going through one of these encounters. Strangest of all was Jupiter. Here, in intricate detail, was the fearsome beauty of the great red Sparta hurricane, 3 times the size of Earth. For some unfathomable reason, it's been raging for more than 300 years. It was great being part of Voyager. A scientist really lives for surprises, discoveries, and Voyager just constantly provided them. I had known about the red spot and the 300-year-old storms, but then, when I saw everything churning and bubbling and very active, it became harder to understand how these large storms could coexist with all this chaos. The Voyagers brought home to Earth images of a majestic world that had tantalized astronomers for centuries, where strange spots glided across the surface, and the clouds swirled like liquid marble. But for every mystery the Voyager spacecraft solved, they uncovered 1,000 more. Voyager was, if you will, just a reconnaissance in force. But when you realize that, for instance, the very best pictures we have of the satellites of Jupiter, from Voyager beautiful as they are no better than what Galileo saw when he turned his telescope to the moon. And think about how much we've learned about the moon since then. It gives you some feeling for why we want to go back. But the Galileo spacecraft hasn't returned simply to take pictures. It also released a small, automated probe to sample Jupiter's atmosphere directly. I stood next to the probe once at Hughes Aircraft, and to stand next to this object which you know is going into the atmosphere of Jupiter, and may become actually part of Jupiter, it's quite an interesting feeling. Quite an exciting feeling. This part of the Galileo mission lasted only 75 minutes, but every minute brought precious discoveries we could make no other way. We hit the atmosphere at about 106,000 miles per hour. That's roughly fast enough to go from San Francisco to New York in less than 90 seconds. This is the most difficult atmospheric entry we've ever done. We have to hit the atmosphere at exactly the right angle. If we hit 1.5 degrees too shallow, the probe will skip out of the atmosphere. If we hit 1.5 degrees too steep, the probe will burn up These difficulties of mission design, though, soon paled with the problem of simply getting Galileo off the ground. We have a cutoff. Galileo was to be the first planetary mission to be launched by a space shuttle. And so, all of the problems with that development were also problems for us. First scheduled for a 1982 liftoff, Galileo missed one appointment with Jupiter after another. Each time, the mission was sent back to the drawing board, and the years slipped by. Then, 4 months before a May 1986 liftoff, the Challenger disaster brought the shuttle program to a standstill. We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that we are. Jupiter had time to wait. Out here, it takes 12 Earth years for the planet to orbit the Sun. Yet it spins so fast that a day on Jupiter lasts less than 10 hours. But what really sets Jupiter apart from the Earth is that beneath its colorful clouds, there are no mountains to view and no solid surface to tread. Unlike the Earth, which is made of solid rock, Jupiter is made of hydrogen gas. It doesn't even have a solid surface at all. We know that it's made of hydrogen because we can weigh it by its gravity, its effect on the moons that go around it, spacecraft that fly past. And it just doesn't weigh enough to be made of something solid like rock. If Jupiter were made solid rock, it would weigh 4 times as much, and its gravity would be even more stupendous. But being made of gas means that even astronomers are reduced to making best guesses about a world so alien, it's beyond our experience. If we could make the impossible journey to the center of Jupiter, we would pass quickly through the turbulent clouds of the atmosphere. But instead of hitting the ground, we would probably dive into a dense miasma of hydrogen gas, thousands of miles deep. As we descend and the pressure builds, the thickening gas is squashed into an ocean of liquid, and deeper still, into metal. Here, in the middle of Jupiter, is a churning sea of metallic hydrogen, generating an immense magnetic aura. It was towards this vast sphere of strangeness that, in 1989, Galileo was finally headed. 5, 4, 3, 2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft, bound for Jupiter. Being lifted into orbit was just the first stage of the most roundabout route that a spacecraft has ever taken to its destination. In the wake of the Challenger disaster, Galileo was released with a smaller-than-planned booster rocket that would only get it as far as Venus in the wrong direction. To get all the way out to Jupiter, Galileo would have to swoop back past Earth twice, each time picking up a gravitational slingshot that would send it a little further out. The whole trip would take 6 years and cover nearly 2.5 billion miles. But the journey Shoemaker-Levy 9 had taken was even longer. 1929 was an auspicious year in astronomical circles. It was the year Carolyn Shoemaker was born, and the year the comet made a critical shift in orbit. After 5 billion years doing lazy circles around the Sun, Shoemaker-Levy was to leave for a new master. 21 years before Carolyn and Gene Shoemaker were to meet the comet they were yet to discover, it strayed too close to Jupiter for comfort and fell under its gravitational spell. On March 22, 1993, David Levy made a familiar trek to the summit of California's Palomar Mountain to join the Shoemakers in a continuing search for comets and asteroids. Well, we'd been having terrible weather the winter of 1993, and we arrived back at Palomar in March. And the first night we were on the telescope was one of those gorgeous, crystalline, dark nights. Marine air had come in over the coastal cities and blanked out the sky glow, and we were all set to go. There's a beautiful, clear night. And I'm loading the telescope and exposing one film, and then another picture, and then a third, and then a fourth, and then Gene Shoemaker calls from downstairs. He said, "David, somebody has opened the film box, and all our film has been exposed to light." Our heart sank because it took 6 hours to prepare the next batch. So I quickly fished out a couple of films from the middle of the box. I tested them in the darkroom, and sure enough, they were light-struck around the outside, but they were still usable in the middle. So we went on and completed the work. Well, the next night, our usual luck started coming back. A storm was coming. We got halfway through, and the cloud stopped us. David, ever the optimist, said, "It isn't that bad. Maybe we ought to keep going." And I said, "No, David. Each one of these films costs us $4 a crack. We can't afford it." And that time, he had an idea. He says, "Don't we have some of that light-struck film left?" I said, "Yes, we do." He said, "Why don't we use those? They're not going to cost us anything. They're ruined anyway. We have nothing to waste but our time." And Gene and Carolyn and I looked at each other, and Gene said, "Let's do it." The very next film that I took with this telescope was the discovery film of Comet Shoemaker-Levy 9. It was another 2 days before they realized what they had found. Carolyn had left the light-fogged plates until last. I returned to David Levy, and I said, "I used to be a person who finds comets." And he sort of plays the violin, feeling sad. And so I went ahead, and I looked at that film and discovered Jupiter was on it, and thought, that's a good omen for me. I found a comet before on a field that had Jupiter on it. I do this very methodically. Started across the top, went back and forth, saw the usual things I expect to see when Jupiter is on a field. And then I came to another something towards the middle of the field. And there was this most amazing image I had ever seen. I turned to the others and said, "I don't know what I've got, but it looks like a squashed comet." Carolyn's strange object needed a second opinion. With fine weather over Kidd Peak in southern Arizona, David Levy called his friend Jim Scotty, working at the Spacewatch telescope. "Hello?" He called me first in the late afternoon, and it was a bit early to do anything about it. When I finally was able to point the telescope at where this weird object was supposed to be, out by Jupiter, I took a scan, and it was apparent that it wasn't just a normal comet. It was a very unique object, with a string of nuclei all in a row. David Levy finally called me back from Palomar. Well, I think he could tell by my tone of voice that something was a little bit out of the ordinary. What had once been a single comet had now become a train of smaller fragments. Could it have gotten too close to Jupiter and been broken up by tidal forces in Jupiter's gravity field? That seemed like an explanation. But we thought, nah, it's not very probable. And I said to myself, fat chance. He always told me I'd never see anything like that. But that's exactly what they had seen. If you're flying along in space, you're weightless. But if you fly past another object, your feet are feeling a little more pulled than your head. And that tends to pull you apart, but very, very gently. And the fact that Shoemaker-Levy got pulled apart by those tidal forces, just like the tides means that it really was not held together very well at the start. Of stronger stuff was Galileo. As it swooped towards Earth for its first gravitational slingshot, haunting signals swept up from thunderstorms on the planet below. Galileo was hearing the sound of lightning bolts rippling into the Earth's magnetic field. As it listened in, the spacecraft picked up the acceleration it needed and left, at 80,000 miles per hour. On the way out, its camera sent back the ultimate home video complete, with glint of sunlight on water. But not every object out here is as well targeted or as well behaved. Jim Scotty takes more than a passing interest in things, moving fast through space. As a Space Watch astronomer, he commutes regularly to the summit of Arizona's Kitt Peak to look for comets and asteroids which might be heading in our. Jim is one of the small, dedicated group of sky watchers looking out for the doomsday asteroid objects bigger than a kilometer, which we think are really the ones that we should most be worried about. That can do the most damage. Given enough time, sooner or later, one of them will hit us. There are something like 1,500 to 2,000 of those objects on Earth-crossing orbits, and we now know something like 100 of them. Certainly, a lot of things out there to run into us. We want to find them all. The odds are that somewhere out there is another big lump of leftover solar system, like Shoemaker-Levy 9, a mile or more across and heading not for Jupiter, but for us. It's happened before. The comet that is thought to have wiped out the dinosaurs was probably about 6 miles in diameter. And history has shown that at the speed these things travel, even a small object is dangerous. The asteroid that crashed at Meteor Crater was no bigger than a 747. 50,000 years ago, this place was a featureless plain, probably with a pygmy forest of juniper and pinyon, and maybe a few larger pine trees out here. The scene that you see behind me, but with trees on it. And then out of the southeast came a brilliant meteor, growing brighter and brighter and brighter, and finally, until it was vastly brighter than the sun. And then it plunged into the earth, creating a shockwave that threw out the rock, making this hole that you can see behind me. And then, of course, material was still carried up in a very large mushroom cloud and came showering back down, making a thin layer of fine material that scattered over the landscape. Back at Mission Control, Bill O'Neill had a more immediate problem to worry about. Galileo's main link with Earth, the high-gain antenna, had been stowed for years longer than planned. Now it had failed to open properly on command. We saw that the motors were drawing more current than they should have, and they kept running beyond the point where the antenna should clearly be open, and were cut off only by the backup computer sequence. So we knew we had a problem. For a while, we were really afraid that we would be very limited in the type of mission we could perform. So we started asking questions and realized that the low-gain antenna actually provided us a lot of opportunity. since we could actually reprogram the spacecraft in flight, if you will, do brain surgery on it, and at the same time utilize our capabilities to improve the systems we have here on Earth, the receiving antennas. And the end result is that we'll be able to do a fantastic amount at Jupiter. My personal interest is in the satellites of Jupiter, and getting a chance to go back and visit these friends again, after having seen them for the first time with Voyager, is a tremendous opportunity. And we're bound to get surprises. After 3 years in space, Galileo had made it as far as Earth for the second and last time. As it picked up acceleration for the final fling to Jupiter, it was within a fraction of a second and half a mile of where it was expected to be. But where was the comet? 2 months after its discovery, no one knew either its exact whereabouts or its final destination. At the Central Bureau for Astronomical Telegrams in Boston, Brian Marston was busy calculating the trajectory of an object that was by now flying out of control. Having been near Jupiter once, of course, it could go near to Jupiter again. And it was on the 22nd of May, 1993, Saturday afternoon, actually, that I felt confident that I knew that it would collide with Jupiter in July 1994, just 14 months later. And it's only 10 minutes to sunset. Whatever astronomical conjunctions had conspired to entrap the comet in Jupiter's powerful spell, the timing could not have been much better. After a daring repair mission to the Hubble Space Telescope, the Earth now had a telescope with unsurpassed clarity of vision. It was amazing that we had warning, so that all of the telescopes around the world could be ready to watch this happen. There were just so many things that were all happening at the right place, at the right time, and all the right people were there to watch it happen. It was really very, very fortunate. This was the most eagerly awaited astronomical event since the return of Halley's Comet in 1986. But that was a non-event. We were all a bit shy because of Comet Halley, so we thought, well, we don't want to overhype this. But we knew there was going to be a lot of very high energy explosions. No one could agree how big the comet fragments were. I didn't really expect much at all, to be honest. But since we used the biggest telescope in the world, we thought, well, maybe we'll get something. Perhaps these so-called pearls on a string were only loose bundles of cosmic crushed ice, which Jupiter would either vaporize or swallow. There was this terrible possibility that Shoemaker-Levy 9 would sink like a rock with nary a ripple. On the week of reckoning, the world's arsenal of telescopes prepared for impact. On mountaintops, in space, and in the air, more lenses were trained on the same part of the sky than ever before in history. Like bombers in formation, Shoemaker-Levy 9 made its final approach. For most people back on Earth, the 16th of July started just as it always did. Here in the foothills of the Sierra Nevada mountains in southern Spain, another sunny day slowly ebbed away most of the locals, oblivious to the drama unfolding in the heavens above. But high on the summit of Calar Alto, the telescopes were waiting, first in line for the view of the millennium. From 400 million miles away, the pre-dawn cloud tops waited. It took 6 minutes for the rising plume to rotate into the sun and into view from Earth. It took another half an hour for the light from Jupiter to reach the telescopes waiting at Calar Alto in southern Spain. 40 minutes after the impact, the mighty flare of a titanic collision was seen for the first time by human eyes. We had heard over the email network that a flash had been seen in the infrared, but we were observing it in visible wavelengths. So we had no idea if we would see anything. And the very first picture that scrolled on the screen there was this amazing impact site. Look at that. And at the same time, there was that little press conference going on, and we could see Gene Shoemaker saying, "Well, we really don't know if we're going to see anything." Surprise in hand, Heidi Hamel interrupted the press conference. Should see these things at all. And I think we may have some up-to-date information. This was the start of a week of spectacular impacts. On the volcanic summit of Hawaii's Mauna Kea, many of the world's finest telescopes swung into action. At the world's largest telescope, the multifaceted Keck, Imadaparta waited, one eye on the monitors, the other on the weather. Well, the weather was absolutely horrible the first few nights. During the G impact, which was the biggest impact, it was just awful. The weather was really bad. And so, at the time of the predicted impact, I called up to the IRF and said, "Well, that's it. We won't see it." And they suddenly said, "Sorry, we have to hang up. You're opening up." So we ran outside, and there was a big hole in the cloud. So we opened up, and we were pointed at Jupiter. And as soon as the shutter opened, we looked at Jupiter, took one image, and Jupiter is right there. And it was this huge fireball on the edge, on the limb of Jupiter. At Siding Spring in Australia, the weather was more kind. We were clear for 8 nights in a row, and so we actually got to see 8 of the impacts. We were actually choosing to observe with an infrared spectrometer. And the spectrometer is an instrument that takes light from Jupiter, then breaks it up into its constituent wavelengths. And you can think of them as colors, even though the human body can't see infrared. They can only feel it as heat. So the beauty of the infrared spectra we were taking was that in that wavelength range, in all those colors, we were able to pick up many, many molecules that are visible in comets and in Jupiter. So we were able to see initially material from Jupiter come up. Things like methane and ammonia we saw first. And then after that, we saw something which was very amazing to us, which was a lot of carbon monoxide and water. Theory had suggested these compounds existed on Jupiter. Now we could see for sure. Waves spread out from that impact, just like ripples in a pond. The speed of the waves depends on how much water you have. And so we were hoping that by measuring the speed of the ripples, we could figure out how much water was on Jupiter. We were surprised because the waves were going faster than we thought. And that meant there was 10 times more water than we expected. From Earth, we saw only the after effects of each collision. But still, a year and a half from Jupiter, one camera had a clear line of sight. Galileo's observations of the impact provided the critical link to this sequence of events. Each fragment punched a hole deep into Jupiter's clouds, perhaps 50 miles below. The fireball exploded, sending a volatile plume of ejecta rocketing back up through the atmosphere. This plume, seen by the Hubble Space Telescope, rose more than 2,000 miles into space. When it crashed back down, it left a bruise the size of the Earth. We were able to see happening in the Jovian atmosphere, right in front of our eyes, the kind of events that we had only speculated about in the past history of the Earth. If you had been in the atmosphere of Jupiter, near the point of one of those impacts, you first would have been buffeted by a tremendous blast. Then, about 20 minutes later, you would have been roasted from the heat of the infalling debris. In the case of the Earth, we believe that this falling material, which fell back over the whole planet, was the primary agent responsible for the death of the dinosaurs. That most of the dinosaurs on the surface would have been roasted within that first hour of the impact. A year later, with the dust settled on Jupiter, the Galileo team prepared for an impact of their own making. Instructions for the orbiter to release the atmospheric probe were all pre-programmed. All mission control could do was wait for Galileo to signal success or failure. If the probe could not be separated, it didn't just mean that we didn't have a probe mission. It also meant we didn't have an orbiter mission, because there's no way we could get the orbiter into orbit with the probe attached. So it was the whole enchilada. The probe had to separate, or it was all over. So it was nervous to the max. Nothing could stop the Galileo mission reaching Jupiter now. For Earthbound scientists such as John Spencer, the postcards Galileo is sending back from the moons of Jupiter will be the next best thing to being there. First, Io. Jupiter's gravity exacts a heavy price for such close proximity. The side of Io that faces Jupiter bulges about 6 miles into the air, and the surface goes up and down by tens of meters every day. That's an enormous amount of distortion of the interior. And it's like taking a paperclip and bending it backwards and forwards, and you generate heat in the place where it's bending. And that exact same process is producing prodigious amounts of heat inside Io. This is a world of monstrous volcanoes and rivers of sulfur. There's 100 times as much heat coming out of every square foot of Io as there is coming out of the Earth. The surface is covered in weird patterns of yellow and brown. Different kinds of sulfur, we think. It's an unbelievable place. Io is only the size of the Earth's moon, yet its largest volcano is twice as big as Texas. If Io is unbelievable, then Europa is enigmatic. There are really strange things on top of the ice. There are curving ridges that have almost perfect geometrical shapes. We can't imagine how those could have formed. When you look at it from a distance, it looks like a cracked eggshell. The surface sort of looks like broken up sea ice on the Earth. That may actually be quite a good analogy, because a lot of people think that there's actually a liquid ocean up beneath the ice on Europa. The core of Europa should be being kept warm by the same tidal forces that heat Io. Underneath the frozen surface may be a warm, saltwater ocean, perhaps 60 miles deep. It's just possible that strange creatures may swim the dark seas of Europa. Some people draw an analogy to black smokers on the Earth's ocean floor, where volcanic heat from the Earth's interior is able to support communities of life, deep down on the ocean floor, 2 miles down. The animals of the Earth's deep sea vents live an alien lifestyle, surviving on sulfur and heat rather than sunlight and plants. If there's anywhere in the solar system where there might still be life other than the Earth, then Europa would be the place to bet. Ganymede is different again, a two-toned world with stretch marks. Ganymede is a very interesting place. It's the largest moon in the solar system. In fact, it's larger than the planet Mercury. Some of the parallel ridges that we see on Ganymede might be similar to some of the parallel ridges we see on a glacier on the Earth. Some areas are covered in strange trenches that snake for thousands of miles across the surface. There's been a lot of activity a long time ago. Most similar to our own moon is Callisto. Callisto is an interesting place because it's not interesting. There's no sign that it's ever done anything in its history except get hit by asteroids and comets and things. And so it's totally covered in craters. And this is weird because it's not too far away from Ganymede, which is a similar size, a similar composition. And Ganymede has a lot of activity on its surface. Callisto is just completely dead. When the probe streaked into Jupiter's atmosphere, it went where no spacecraft had gone before. One of the surprising findings has been Jupiter appears to be depleted in water. And we're really going to have to understand whether that's a global phenomenon or just the fact that we went down near the equator, and that's depleted in water. Either way, it's a fundamental discovery that we're going to have to understand. We discovered that the winds are much larger than we had anticipated. And it appears that the winds increase as the probe was going down deeper into the atmosphere. We wanted to know how many cloud layers there were. We expected to find 3. We only found 1. And we still have not yet identified the composition of that cloud layer. That's also been a major surprise. What it's telling us is that Jupiter is different than we'd anticipated. And we're going to have to revise some of our theories about how planets formed, what the early solar system was like, and eventually that feeds back to understanding how the Earth evolved and formed also. Some 75 minutes after it entered the atmosphere, the probe's mission was over, having reached a depth of more than 100 miles. Like the comet before it, but without the fireworks, the probe became just another old piece of solar system, sucked up by the gas giant. Jupiter is the solar system's vacuum cleaner. If Jupiter weren't there, those comets would still be running around, smashing into all of the inner planets, including the Earth. The Earth would be being hit by comets instead of once every 100,000 years, might be being hit every 100 years or every 1,000 years. And we couldn't be here. We couldn't live on an Earth that was being smashed by a comet every 1,000 years. For far longer than we've been aware, Jupiter has been playing the cosmic Hoover its massive gravitational power, safeguarding our planet, long enough for the human race to arise, and for people like Galileo to ask questions of the heavens above. The Galileo orbiter will end its days here, in endless circles of the king planet, telegraphing answers for as long as its power supplies last. For 5 billion years, Jupiter has kept its secrets to itself. Now, in the closing years of the 20th century, we are finally discovering what our most important neighbor is really like.